Welcome to this coding session. Today, we'll be exploring LeetCode problem number 1362, closest divisors. This problem challenges us to find two integers whose product equals either number plus 1 or number plus 2, with the goal of minimizing their absolute difference. Let's dive in and break it down step by step. In this problem, you're tasked with finding two integers, a and b, such that their product is equal to either number plus 1 or number plus 2. The goal is to minimize the absolute difference between a and b. You can return the pair, a, b, in any order. If there are multiple valid pairs, any of them can be returned. The input is an integer number that ranges from 1 to 10 to the power of 9. For the output, you'll return a list containing the pair, a, b. The challenge lies in not only finding valid divisors but also ensuring that the pair you choose has the smallest possible difference between the two numbers. For example, if number is 8, we need to find divisors of number plus 1, which is 9, or number plus 2, which is 10. For 9, the divisors are 1, 9, and 3, 3. Among these pairs, the absolute difference a-b is smallest for 3, 3, where the difference is 0. For 10, the divisors are 1, 10, and 2, 5. Here, the pair 2, 5 has a difference of 3. Since the smallest difference overall is achieved with the pair 3, 3, the output is 3, 3. Now consider number equals 123. In this case, we examine divisors of number plus 1 equals 124 and number plus 2 equals 125. For 124, divisors include 1, 124, 2, 62, and 4, 31. For 125, divisors are 1, 125, and 5, 25. The pair 5, 25 has the smallest difference, 5, 25 equals 20, so the output is 5, 25. Now let's look at another example where number is 999. Here, we need divisors of number plus 1 equals 1000 and number plus 2 equals 1001. For 1000, there are several divisor pairs, such as 1, 1000, 2, 500, 4, 250, 5, 200, 8, 125, 10, 100, 20, 50, and 25, 40. Among these pairs, 25, 40 has the smallest absolute difference, which is 25, 40 equals 15. This makes it the closest pair for number plus 1. For number plus 2 equals 1001, the divisors are 1, 1001, and 7, 143. The smallest difference here is 7, 143 equals 136, which is much larger than the difference for 25, 40. Therefore, the output for this example is 25, 40. The problem also has several important constraints and edge cases. The value of number can range from 1 to 10 to the power of 9, so your solution must be efficient enough to handle very large inputs. For instance, when number is at its smallest value, 1, the divisors of number plus 1 equals 2 are 1, 2, and the divisors of number plus 2 equals 3 are 1, 3. In this case, the output could be 1, 2, or 1, 3. At the upper limit, when number equals 10⁻9, the numbers number plus 1 and number plus 2 are extremely large, so efficient divisor finding algorithms are critical. Another edge case arises when number plus 1 or number plus 2 is a prime number, as the only valid divisors in such cases are 1, number plus 1, or 1, number plus 2. Handling these scenarios efficiently while ensuring the smallest difference makes this problem an interesting challenge. To solve the problem of finding the closest divisors for a given number, we need to focus on two critical conditions. First, the product of two integers, a and b, must equal either number plus 1 or number plus 2. Second, the absolute difference between these two integers, a and b, needs to be minimized. These requirements create a dual challenge, satisfying the product condition while ensuring the divisors are as close as possible. To tackle this, we need to evaluate different approaches that balance these goals effectively. One straightforward way to approach this is through brute force. Here, we iterate over all possible divisors a from 1 to the square root of number plus 2, checking if it divides either number plus 1 or number plus 2 without leaving a remainder. If it does, we calculate the corresponding value of b, which is either number plus 1/a or number plus 2/a, and then track the pair with the smallest difference a and b. The key insight here is that divisors always come in pairs, and the closer these pairs are to the square root of the number, the smaller their difference will be. This is why the search is limited to the range up to the square root of number plus 2. Although this method is simple and computationally manageable due to the limited range, it does require separate checks for both number plus 1 and number plus 2, which introduces some redundancy. To improve on this, we can adopt an optimized approach that reduces redundant checks. Instead of looping separately for number plus 1 and number plus 2, we combine the search into a single pass. For each potential divisor A within the range of 1 to the square root of number plus 2, we first check if A divides number plus 2. If it does, we calculate the pair and update the closest pair if the difference is smaller. If not, we then check if it divides number plus 1 and repeat the process. By starting the search from the square root of number plus 2 and moving downward, we can stop as soon as we find a valid pair, as divisors near the square root are more likely to yield minimal differences. This approach avoids redundant iterations and is computationally efficient, maintaining the same time complexity of sqrt number, but eliminating unnecessary repetition. The optimized approach is the most effective strategy for this problem because it achieves a good balance between simplicity and performance. By iterating only once and prioritizing divisors near the square root of number plus 2, we minimize computational overhead and ensure correctness. When comparing the brute force and optimized approaches, the brute force method is easier to implement but involves redundant checks for number plus 1 and number plus 2, leading to a slight increase in runtime. Alternative methods, such as pre-computing all divisors, would be memory-intensive and unnecessary for large inputs. The optimized approach avoids these pitfalls, making it ideal for competitive programming scenarios where both clarity and efficiency are crucial. The problem here is to find two integers, a and b, such that their product equals either number plus 1 or number plus 2, and the absolute difference between a and b is minimized. To solve this, we need to focus on finding divisor pairs for the numbers number plus 1 and number plus 2. A key observation is that divisors of a number always come in pairs. If a asterisk b equals target, then a and b form one such pair. The closer a and b are to each other, the smaller their absolute difference will be. This happens when the divisor pair is near the square root of the target. To begin, we define our targets. Target 1 is number plus 1 and target 2 is number plus 2. These are the two numbers for which we'll look for divisors to determine the pair with the smallest difference. To efficiently find the closest divisor pairs, we start by iterating from the square root of the target down to 1. This approach ensures that we quickly identify pairs with minimal differences because divisors near the square root tend to be the closest. For each divisor I in this range, we check if I divides the target without a remainder. If it does, the corresponding pair is a equals I and b equals target slash I. At this point, we compute the absolute difference, a/b, and compare it with the current smallest difference. If this new pair has a smaller difference, we update our best pair. This process is repeated for both target 1 and target 2. Once we've checked all divisors for both targets, the final pair with the smallest difference is chosen and returned as the result. The algorithm is built on a few important insights. First, divisors of a number are symmetric around its square root. For example, with n equals 36, the divisors are 1, 36, 2, 18, 3, 12, 4, 9, and 6, 6. This symmetry allows us to restrict our search to numbers up to the square root, significantly improving efficiency. Second, because we are considering number plus 1 and number plus 2, we need to evaluate both targets since the optimal pair could belong to either one. Efficiency is further enhanced by iterating downward from the square root, minimizing redundant checks. We use two key variables, best_diff to track the smallest difference encountered, and best_pair to store the corresponding divisor pair. The time complexity of this approach is sqrt number, as we only iterate up to the square root for each of the two targets. The space complexity is 1, because no additional data structures are required beyond a few variables. Let's go through an example to see the algorithm in action. Suppose the input number is 8. First, we calculate target 1 equals 8 plus 1 equals 9 and target 2 equals 8 plus 2 equals 10. Starting with target 1, we check its divisors. The square root of 9 is 3, so we begin with I equals 3. Since 9% 3 equals 0, we find the pair 3, 3, with a difference of 0. This becomes our current best pair. Next, for target 2, the square root is approximately 3, so we start with I equals 3. Here, 10% 3 equals 0, so we decrement I to 2. Now, 10% 2 equals 0, giving the pair 2, 5, with a difference of 3. Since this difference is larger than our current best difference, we don't update the best pair. Comparing the results, the closest divisors are 3, 3, from target 1. The output is 3, 3. This Python implementation solves LeetCode problem number 1362 closest divisors efficiently. The goal is to find two integers whose product equals either number plus 1 or number plus 2, minimizing their absolute difference. Explanation. 1. Helper function, find closest divisors, target. This function identifies the closest divisors of the input target. It starts iterating from the square root of the target downward. This is because numbers closer to the square root are more likely to produce pairs with minimal differences. For each integer I, it checks if I is a divisor of target, i.e., target % I equals 0. If true, it returns the pair, I, target // I. 2. Main function, closest divisors, number. The function computes the closest divisors for both number plus 1 and number plus 2 using the helper. It stores the divisor pairs for number plus 1 in divisors 1 and for number plus 2 in divisors 2. 3. Comparison. Between divisors 1 and divisors 2, it compares the absolute differences of the two integers in each pair. The pair with the smaller absolute difference is returned as the result. Efficiency. The time complexity is approximately O(sqrt) number, because the iteration in find closest divisors is bounded by the square root of the target. This solution is efficient and handles edge cases effectively, as the logic ensures that both number plus 1 and number plus 2 are considered. By following this approach, we ensure the optimal solution for finding the closest divisors of number plus 1 or number plus 2 with minimal difference. This is the Java implementation of the LeetCode problem number 1362, closest divisors. The logic mirrors the provided Python solution, with adjustments for Java syntax and conventions. The closest divisors method computes the closest divisors for numbers number plus 1 and number plus 2 using a helper method. It then compares the divisor pairs based on the absolute difference between their values. Key differences include explicit type declarations, the use of math.sqrt for square root computation, and array handling in Java. To solve this problem, we start with the input number equals 8. Our goal is to find the closest divisors for numbers number plus 1 and number plus 2, which in this case are 9 and 10. First, we evaluate the divisors for 9 by calling the find closest divisors function. We begin iterating from the square root of 9, which is 3, and check if 9 is divisible by 3. Since it is, we identify the divisors as 3, 3, and return this result. Next, we evaluate the divisors for 10. Again, we start iterating from the square root, which is 3. Checking divisibility, we find that 10 is not divisible by 3, so we decrement to 2. At this point, we see that 10 is divisible by 2, giving us the divisors 2, 5, which we return. Now that we have the results for both 9 and 10, we compare the closest divisor pairs. For 9, the divisors 3, 3 have an absolute difference of 0, while for 10, the divisors 2, 5 have a difference of 3. Since the pair 3, 3 has the smaller difference, we return it as the result. Moving on to the next example, we now consider the input number equals 1. Here, we need to find the closest divisors for number plus 1 and number plus 2, which are 2 and 3. Starting with 2, we call find closest divisors and begin iterating downwards from the square root, which is 1. We find that 2 is divisible by 1, giving us the divisors 1, 2, which we return. Next, we evaluate the divisors for 3. Calling the find closest divisors function, we again start iterating from the square root, which is 1. Checking divisibility, we find that 3 is divisible by 1, resulting in the divisors 1, 3, which we return. Comparing the two results, the divisors 1, 2 have an absolute difference of 1, while the divisors 1, 3 have a difference of 2. Since 1, 2 has the smaller difference, we select it as our result. Thus, for number equals 1, the output is 1, 2. For the final example, we take the input number equals 999. Here, we calculate the closest divisors for number plus 1 and number plus 2, which are 1000 and 1001. Starting with 1000, we call find closest divisors and begin iterating from the square root, which is 31, moving downward. After checking several values, we find that 1000 is divisible by 25, yielding the divisors 25, 40, which we return. Next, for 1001, we again start iterating from the square root of 31. After checking various values, we find that 1001 is divisible by 7, giving us the divisors 7, 143, which we return. With both results in hand, we compare the divisor pairs. For 1000, the divisors 25, 40 have an absolute difference of 15, while for 1001, the divisors 7, 143 have a difference of 136. Since 25, 40 has the smaller difference, we select it as our result. Therefore, for number equals 999, the closest divisors are 25, 40. The time complexity of this solution revolves around the find closest divisors function, which is the core computational step. This function is called twice, once with number plus 1 and once with number plus 2. Within find closest divisors, we iterate from the square root of the target down to 1, checking if I is a divisor of the target number. The reason we only iterate down to the square root is because divisors always appear in pairs, so once we pass the square root, we've already accounted for all possible divisor pairs. For each iteration, we perform a modulo operation, which is constant time, or O1. Since the loop runs approximately sqrt, target, times, the complexity of one call to find closest divisors is O, sqrt, target. Because this function is called twice, the overall time complexity becomes O, sqrt, number plus 1, plus O, sqrt, number plus 2. Simplifying this, we get O, sqrt, number, as the growth rate is dominated by the square root of the input size. The space complexity of this solution is O1, meaning it requires a constant amount of memory regardless of the input size. The find closest divisors function uses a fixed number of variables, such as the loop variable I and the pair of divisors that is returned. No additional data structures like arrays or hash maps are needed, so the memory usage remains unaffected by the size of the input. Now, let's consider the best, average, and worst case scenarios for this algorithm. In the best case, even if number is small, the loop in find closest divisors still iterates up to the square root of the target, resulting in O, sqrt, number. For the average case, the behavior remains the same since the number of iterations always depends on the square root of the input. In the worst case, such as when number is very large, the same logic applies. The time complexity remains O, sqrt, number, across all cases, as it fundamentally depends on the square root of the input. When comparing this solution to a brute force approach, the efficiency becomes even more evident. A naive method would involve iterating through every integer from 1 to the target to find divisors, which takes O, target, time for each target. Since the brute force approach checks both number plus 1 and number plus 2, the total time complexity would be O, number plus 1, plus O, number plus 2, or simply O, number. On the other hand, the optimized solution reduces this significantly to O, sqrt, number, by utilizing the mathematical property that divisors only need to be checked up to the square root of the target, thanks to the pairing of divisors. To further validate this, the number of iterations in find closest divisors is directly proportional to the square root of the target, as each divisor below the square root corresponds to a unique counterpart above it. This divisor pairing property ensures we only iterate up to sqrt, target, and since this applies to both number plus 1 and number plus 2, the overall complexity remains O, sqrt, number. When solving this problem, there are several common mistakes to watch out for. First, it's important not to ignore either of the two candidates, number plus 1 and number plus 2. The problem allows you to use either, so failing to check both could result in missing the optimal solution. Next, an inefficient search range is another frequent issue. Some solutions mistakenly iterate all the way from 1 to the number itself, which is unnecessary. By iterating only up to the square root of the number, you can significantly reduce computations, as divisors always come in pairs. Additionally, edge cases like number equals 0 or very large values near the upper limit, such as 10⁻⁹, can expose issues with bounds checking or integer overflow in certain languages. Finally, another mistake to avoid is incorrectly calculating the absolute difference between divisors. If you forget to take the absolute difference or compare the divisors in the wrong order, it can lead to incorrect results. Another mistake to be aware of is mixing up the return values. For example, you might accidentally return the divisors from number +1 instead of number +2, even when the latter pair has a smaller difference. This typically happens when conditions in your code aren't carefully checked. Now, let's talk about some insights that are particularly relevant for interviews. Recognizing patterns is key. This problem revolves around the concept of divisor pairs, so understanding that divisors come in pairs, such as a*b equals number +1, is crucial. Interviewers often look for candidates who can identify this and use it to optimize their approach. Speaking of optimization, this problem is a great opportunity to demonstrate an optimization mindset. Instead of brute forcing through all numbers, iterating only up to the square root is a classic and efficient technique that interviewers appreciate. Also, be ready to discuss edge cases. For instance, you might need to explain how your solution handles the smallest possible values of number, as well as its largest. Finally, you should be able to justify why a specific pair of divisors was chosen and compare results efficiently to ensure correctness. This problem also connects to several related problems that you might encounter. For instance, LeetCode 507, the perfect number problem, involves checking whether a number is perfect by summing its divisors. Similarly, LeetCode 263, ugly number, focuses on divisors and factorization, specifically determining if a number is composed only of certain prime factors. Another related problem is LeetCode 1712, ways to split array into 3 subarrays, which, while not directly about divisors, shares a conceptual similarity in minimizing absolute differences when splitting or partitioning. Lastly, LeetCode 233, number of digit 1, deals with efficient computation under constraints, highlighting optimization techniques that carry over to problems like closest divisors. Now let's compare some alternative approaches and the trade-offs involved. The brute force approach involves iterating through all numbers from 1 to number +1 and number +2 to check for divisors. While simple to implement, this method is inefficient for large inputs due to its O(n) complexity. A more efficient approach is the optimized search using the square root. Here, you iterate only up to the square root of number +1 and number +2 to find divisor pairs. This reduces the time complexity to O(n) while ensuring correctness, but it requires a solid understanding of divisor properties. A less common approach is pre-computation, where you calculate divisors for a range of numbers ahead of time. While this can answer queries quickly, it comes with high memory usage and setup time, making it impractical unless you're handling multiple queries over the same range. Each approach has its own use case, so choosing the right one depends on the problem constraints and performance requirements. Great job! To summarize, we tackled the closest divisors problem by leveraging efficient factorization techniques to find the solution in O(n) time. Remember, mastering divisor-based problems requires both mathematical insight and algorithmic thinking. Thanks for joining me today. Be sure to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!